Hello everyone, myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So, in the previous session, we have seen the shear flow in open section beam problems. We have seen channel section problem and we have seen Z section problem. And again in channel section problem, which is open section, we have seen how to calculate the position of shear center. Now we are extending our discussion from open section to closed section. So now in this present module, we are going to see what is the shear of closed section beams and probably define what is shear center again. So the learning outcomes in this module, the students are able to understand the solve shear center of closed section beam problems. And so shear of closed section beams. Now we see in the open section beam formula, that is Qs equals to minus of Sx Ixx minus Sy Ixy by Ixx Iyy minus I square xy integral 0 to S Tx into ds minus Sy Iyy minus Sx Ixy divided by Ixx Iyy minus I square xy integral 0 to S Ty into ds. So from here to here, it is nothing but the formula of open section beams. So that we are assuming it as QB. So QB is nothing but open section beams. Now, the only difference for open section, for example, if you consider channel section. So 3 walls we are having here for channel section. The 4th wall is open. So this you are considering it as open section beam. Now, even if the 4th wall is also closed, now this you can consider it as closed sections beam. Okay. So whether it may be rectangle, whether it may be circle, semicircle, whatever it is. So if all the walls of the section are closed, then you will consider that beam as closed section beam. So the procedure here slightly differs because open section beam calculation of shear flow is a straightaway problem. Straightaway you can calculate the shear flow distribution for open section beams because it is determinate structure, whereas the closed section beam is indeterminate structure. Okay, so it is little the another equations, additional equations are required in terms of displacement to solve these kind of closed section problems because they are indeterminate structures. Okay, so since one more wall is we are adding here, so to make the section as closed, or for closed section beams, what we are adding here is nothing but QS0. So QS0 is called as constant shear flow. You can consider it as additional constant shear flow. So QB is the open section shear flow, QS0 is a constant shear flow, and therefore the shear flow distribution QS is the combination of QB plus QS0. So this together will call the shear flow distribution for closed section beams. Okay, so QS equals to QB plus QS0, and this additional constant shear flow QS0 can be calculated using the formula, that is minus of cyclic integral of QB by QB into ds divided by cyclic integral of ds. So that is how you calculate the additional constant shear flow, that is QS0, and once you calculate this, you have to add to here for the existing open section shear flow. Okay, also you have to understand that there are two problems in this. One is the open section problem and other one is the closed section problem. So if you have got like this, so if you have a problem like this, directly you can put it in the formula for open section beams QB, and you can find out the shear flow distribution here straight away. Okay, but whereas here this is, as we discussed, is the indeterminate structure, closed section. So what we have to do in this kind of problems is you have to assume that any wall is open, and you are considering that QS0 equal to 0. You have to make a cut in any one of the wall, and then this will become open section beam. And for example 1 2 3 4 is there, so 4 1 you are making a cut and you are making it as open, so you are assuming that QS0 is 0 in this wall. 1 4 is 0 you are assuming. Okay, and then you calculate rest of the shear flows because they becomes open section shear flows. So QB 1 2, QB 2 3 and QB 3 4, this becomes open section shear flows. And once you get this open section shear flows, what you have to do is, so first this is the panel and this we are making cut here, then you have to add additional constant shear flow, that is QS0 everywhere for all the walls. What is that? QS0, 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 QS0. Okay, why we are adding that? Because if we don't make a cut here in the closed section, there would have been some shear flow in this wall also. Okay, but what we are doing, we are making a cut, making it as open, we are assuming it as 0 and calculating the rest of the shear flows, and you calculating rest of the shear flows 1 to 2, 2 to 3, 3 to 4 by assuming this as open. Now since if there is no cut that is made over in 1/4, there would have been some shear flow in this wall also. Now that, what is that shear flow? So that is what we are calculating by adding this QS0. Okay, so and after adding this QS0, and anyway loads will be there that may act here at 3, that is SY load, and you have to consider moment about a suitable point and you have to equate to 0. When you consider moment about suitable point and equate to 0, then you are going to get this additional constant shear flow QS0. Okay, so once you get this QS0, and you have to superimpose onto this diagram to get the actual shear flow. So you have to add this QS0 to all these QB values, QB12 plus QS0, QB23 plus QS0, QB34 plus QS0. Then it becomes the actual shear flow. Sometimes if they are both in the same direction, it may add, and if they are in the opposite direction, it may subtract. So, but after adding QS0 to this QB values, then you get the actual shear flows, that is Q12, 2, 3, 3, 4. Okay, this is how we basically do the closed section shear flow problem. Okay, procedure. Okay, so again it depends for problems to problems. The procedure also slightly varies from problem to problem, but this is a regular procedure what we do for the solving the shear of closed section beams problems. Rest of all the thing is same like closed section, open section beams. Okay, the only thing is what you have to consider the additional constant shear flow in the analysis, right? So to understand that, we'll see one problem here, and you can see here a thin walled closed section beam has the singly symmetrical cross section shown in figure. Each wall of the section is flat and it has the same thickness T and same shear modulus, that is capital G, and he is asking to calculate the distance of shear center from point 4. Where is point 4? And here it is point 4. He is asking to calculate the distance of shear center. So the diagram he has given, but let's try to understand that. So what he has given is, rather than looking into this problem diagram directly, let's try to understand this diagram. So we know the formula, and the given section is symmetrical about horizontal axis. Okay, and if the symmetrical about horizontal axis, and we know that the formula for shear flow reduces, and because again also since the given section is symmetrical about horizontal axis, we'll substitute Ixy equals 0, and he is asking to calculate the distance of shear center. So shear center, since the given section is symmetrical about horizontal axis, the shear center lie anywhere on this horizontal axis. So you need to calculate only the horizontal position of shear center. Okay, and the distance he has given, the horizontal position of shear center is asking to calculate from point 4, and he is giving the distance horizontal shear position of shear center from point 4 as zeta s. So you need to calculate only the horizontal position of shear center. So we know that we discussed in the previous session as well that to calculate the horizontal position of shear center, we have to assume a vertical load. Okay, so when you assume vertical load and horizontal shear load, you can substitute 0, and with this Ixy equal to 0 and Sx equals to 0, our formula for this one, this completely goes to 0, and here this term goes to 0, this term goes to 0, and you left with Qs equals to minus Sy by Ixx integral 0 to S T into Y into ds plus Qs0. So this is the formula that we'll use for solving the problem. Okay, so after substituting here, what you're going to get? You're going to get this equation, that is Qs equals to minus Sy by Ixx integral 0 to S T into Y into ds plus Qs0. Okay, so this you can consider it as equation number 1. Okay, now here what you need to calculate is here Ixx. Okay, Ixx for the complete section. Okay, so Ixx for the complete section, but here you can see that here we don't have any horizontal wall, or here we don't have any vertical wall. Instead of that, we got inclined walls. Okay, so inclined wall 1 2, inclined wall 2 3, inclined wall 3 4, and inclined wall 4 1. So all the walls that are there in the diagram, so all that walls are inclined. And even we have seen the procedure how to calculate moment of inertia, because for this problem you have to calculate moment of inertia. So though it may be symmetrical about horizontal axis, you can consider that twice, and you can consider any of the two walls either above or below. So if you try to calculate above or below walls, so you have to consider the moment of inertia for wall 1 2 from here to here, then moment of inertia for wall 1 4, that is here to here. Okay, but calculating moment of inertia for 1 2 inclined wall and 1 4 inclined wall, it's very very important. Okay, I hope you remember that in the previous unit, in the last session, we have seen how to calculate the moment of inertia for the inclined walls and the curved walls. Okay, so that concept we need to use here. Okay, so we have seen that their problem ixx equals to integral 0 to s into t into y square into ds, that we have used. And for y we substituted s into sine beta. Okay, and substituted in the formula, and we got the formula as th cube something sine square alpha or sine square beta by 12, like that we got moment of inertia for the inclined section. Now similar kind of procedure we have to adapt here. Okay, so as we discussed here, ixx is the combination of both ixx12 plus ixx14 multiplied by 2. Now that we have to see here, same thing here we are going to see here. So ixx2 into, and for the first one 0 to 10a. Now what is that wall 0 to 10a? And here also again, here we have 9a, this is 9a, this is 6a. Okay, so total if you try to make a right angle here, and this is 15a together. Okay, so this is 15a and this is 8a. Okay, so 225 and this one is 64, and what you get here is nothing but this is, you're going to get 17a. Wall 1 2 length, wall length 1 2, you're going to get a 17a. Similarly, when you try to take only this triangle, and here we got 6a and here you got 8a, so here you are going to get 10a. Okay, so the wall lengths that is 1 4, and that you are going to get as 10a, and this you are going to get as 10a, and this is 2. Okay, so that you have to understand here 10a. So for the problem, and first is taken as 10a and t into y square ds. Okay, so this is 6a, this is 8a, for if you consider this one. Okay, now we have to consider the distribution. Now what you have to do here, it is the distribution you have to consider. So from here to here you have to consider the distribution as s1. Okay, s1 as a distribution, or in the diagram he is given directly the distribution. Here to here he has given s1 is a distribution. Okay, so when you take the distribution, what you have to substitute is t into y square into ds1 you have to substitute. Okay, and that triangle, if you try to consider, this is the distribution he considered s1, and this is 8a and this is 6a, and anyway this is 10a. We are considering the distribution anyway, that you can substitute in the limits. Okay, and the angle, what is the angle he considered here in the diagram? This is the angle, that is theta 2. So theta 2 is the angle that he considered. Okay, and what we have to substitute, t into y square into ds, we need y. Okay, so you can consider this as x, this as y, and apply here sine theta 2, that is equals to opposite side, that is yeah. So instead of considering sine, now you consider we want this length. So you have to consider cos theta 2. Okay. So we want the vertical distance, right? So we want y. To substitute y, we have to substitute cos of the angle. So cos theta 2, that is equals to 8a by 10a, isn't it? So this is 10a, 8a by 10a, that you have to substitute, and this will get cancelled, and in terms of s1 you have to substitute. So t y square dx, so that you are going to get is nothing but what, 8a by 10a into s1. So you have to write it as, to get that one, or else simply you can substitute cos theta 2, that is equals to y by s1. So y equals to s1 cos theta 2, and from the diagram, yeah, you can go like this. So cos theta 2 equals y by s1, y equals to s1 cos theta 2, and you can simply consider s1 into y, you can substitute 8 by 10. Okay, so now that is being taken and substituted here for 8 by 10 into s1. Okay, similarly for the second diagram, you have like this, and this is 17a, and this is again 8a, and this is 15a, and this is the angle theta 1, and again you can consider cos theta 1, this is y, and this is s2, and you can consider y by s2 or y2 by s2, and so that y2 is equals to s2 into cos theta 1, and where cos theta 1 from the diagram is nothing but is equals to 8 by 17, or 8a by 17a, a gets cancelled, so you get s2 into 8 by 17. So that you have to substitute over here. Okay, so cos for y1 here, y1 square, you can substitute 8 by 10 s1, and for y2 you can substitute 8 by 17 s2, and you integrate between the limits 0 to 10a and 0 to 17a, you are going to get ix6, that is equals to 1152 into a cube into t. Okay, so once you get this ix6, take and substitute over in the formula for qs in equation 1. So qs is equals to minus sy by ix6 integral 0 to s t into y into ds plus qs naught. Okay, so once you substitute here, what we need to do here, it is the basic shear flow distribution qb is obtained from equation, first term in the equation 1. So this is what up to here, from here to here is qb, and here it is qs naught. So this is the open section shear flow. So if you want to calculate the open section shear flow, that can be obtained from the first term in the equation 1, that is this equation. Okay, so let's try to substitute that for qb 41, first 41 wall we are considering, 41, which is 41 wall. So for this one we are considering. Okay, so for 41 wall, because it is a closed section and all are closed walls, so what we are doing here, for example, you can consider, you can make a cut in wall 43, and you can assume qs 43, you can assume it as 0. Okay, so that this will become open. Now you are calculating the open section shear flow qb41. Okay, so after qb41, then you have to go with qb12. Okay, these two are sufficient because of symmetry, and you can write rest of the things as it is. So when you do that, qb41, that is equals to, and substituting all this 1152 by a cube, 1152 a cube t over here, and you get minus sy by 1152 a cube t integral 0 to s, means integral 0 to s1 into t into y into ds. So t into, again what is y, 8 by 10 s1 for the wall 41 into ds1, that is equals to minus sy 1152 by a cube, and this 8 by 10 it becomes 2 by 5, and now here t into integration of s1, integration of s1 becomes s1 square by 2. Okay, so the 2 also gets cancelled, so you get qb41 as minus sy by 1152 a cube into 2 by 5 into s1 square. Okay, so once you get this qb41 wall, next let's try to find out the shear flow in the other wall also. What is that other wall? The other wall is 1 2. Okay, qb41 is over, next we have to go with 1 2. So for doing 1 2, we are considering the distribution as s2 over here. Okay, s2 distribution here, from here to here. So For that S2, same thing, you substitute minus sy by 1152a cube integral 0 to S2, and what you have to substitute here, it is very, very important, in place of y. Okay, because in the formula we got y ds. Okay, so what is that y ds here is nothing but, that you have to consider it as, it's very, very important to understand this. Okay, this particular term, for since this is wall 4-1 wall, we substituted 8 by 10 S1 because directly we are taking the distribution. For S1 we are taking the distribution from the axis itself. So directly we have written the distribution as 8 by 10 S1 as we got it as from y directly. Okay, but whereas for this distribution S2, it is taken here, and first of all the total length is 17a. Okay, so the distribution from here to here, it becomes 17a minus S2. This we have to consider first, and then followed by the angle, that is y distance. What is that y? We got 8 by 17. In fact, 8a by 17a, 8a will get cancelled. So what we have to write here, it is 17a minus S2 into 8 by 17 also we have to multiply, because it is the inclined distance, but what we discuss is vertical distance y. Okay, so that you can write this as, you can write this as 17a minus S2 into 8 by 17 ds2. Okay, plus what is added here, 40a square. Now from where this we got 40a square? This we got from the previous one. Okay, so that you have to calculate here, and after this QB41. So like at 4 S1 equal to 0. When you substitute S1 equal to 0, you will get the starting shear flow Q4 equal to 0. And at 1, you have to substitute S1, that is equals to, and how much distance it is covering, 10a. Okay, so at 1, if you are calculating, substitute 10a here, and you are going to get Q1. So in place of S1 square, you substitute 10a whole square, that is it becomes 100a square, and a square here it gets cancelled, and when you calculate this one, you are going to get 40a square, and that we have to add here as the starting shear flow over here. Okay, so QB12 you have to substitute like that, and then you are going to get 40a square here. So that you have to add, because for QB41, it is a starting shear flow that you are making cut as here, and you are making it as 0, so that it will be 0. But whereas for calculating 1, 2, the starting shear flow would be 1. So Q1 you have to evaluate from QB41, and then you have to add to this Q12. Okay, that you should not forget. So we are adding here, and once you add here, you are going to get, after integration, QB12 equals to minus sy divided by 1152a cube into minus 4 by 17 s2 square plus 8a s2 plus 40a square. So this is second equation we got from QB12. Okay, so one equation distribution we got from the equation number 2, that is QB41. Other equation we got is QB12, that is distribution. But we should not forget our aim to calculate the shear center. Okay, so to calculate the shear center, what we get here is the QB distribution, and you have to take the moment about before you calculate the shear center position. So that QB distribution, since wall 2, 3 and 3, 4 follow from symmetry, hence from that equation you can calculate QS0, and QS0 is equal to, what is that equation? QS0, that is equals to minus cyclic integral of minus cyclic integral of QB ds divided by cyclic integral of ds. Anyway, cyclic integral of ds is nothing but it's all wall lengths. So all wall lengths, and if you look at it here, this is 10a, this is 10a, 20a, and this is 17a, and this is 17a. So that is 34a. So 34a plus 28. So you are going to get the total wall length for this is 54a. So that you are going to substitute here. So that is 54a you substituted here in the denominator, and rest of all the procedure is nothing but, it is a, and I think minus here we got, minus, that is right. So rest of the procedure is nothing but it is a QB into ds. What is QB into ds? So we got QB12, and on the, for example, you got like this 4 1 2 3, and you are concentrating only on the upper half, and so that first you write QB 41 into ds. What is this length on which, what is the length of this one? That is 10a. So that you have to, instead of writing 10a, I am taking integral over here, integral 0 to 10a, and then writing it as ds1, and then plus the second one 1 to 2. 1 to 2 is again integral 0 to 17a, and writing QB12 into ds1, okay, into ds2. That's it on the numerator. So we are replacing QB41 values, QB12 values, what we got from the previous equation, that is equation 2 and equation 3. We are taking them and substituting in this equation in place of QB41 and QB12. Okay, so once to substitute and integrate it between the respective limits 0 to 10a, 0 to 17a, and we will left with the QS naught, that is equals to SY by 1152a cube into 58.7a square. So this is the additional constant shear flow. If the cut is not made, this would have been present in the analysis. Okay, now this we calculated. First we assumed that we made a cut, now we calculated it from the formula QS naught equals to minus of cyclic integral of QB ds divided by cyclic integral of ds. So once you do this QS naught, then you can apply the moment about any particular point, and then you can equate the moment due to the external load to the moment due to the shear flow. Okay, and you are taking, we are considering moment about 0.2. Now it's very important again to understand for us, like we have diagram like this, and this is 4 1 2 and this is 3. Okay, and this is somewhere here we considered shear center, and here we assumed SY, and from here to here we have assumed it as zeta s. Okay, and total length is nothing but 15a, that is from here to here 6a, and here it is 9a. Okay, now we are taking moment about 2. Now when you take moment about 0.2, first you write moment due to SY. So SY into moment about 0.2 means from here to here, this will be the perpendicular distance from here to here. So from here to here it is zeta s, and from here to here it is 9a. So zeta SY into zeta s plus 9a is the moment due to the shear load on the left side. Okay, and on the right side you have to write moment due to shear flows. Now how many walls are there? 4 1 is one wall, 1 2 is one wall, 2 3 is one wall, 3 4 is one wall. Out of which what you can do here, it is you can consider by symmetry, and also since you are considering moment about 0.2, the shear flows passing through 1 2, shear flows passing through 2 3 doesn't give any moment because the perpendicular distance is 0. So the moments that you give is nothing but the shear flows that will give moment is 4 1 and 4 3 will give moment about 0.2. Okay, and also since 4 1 and 4 3 are identical, that is equal because of symmetry, so you can just multiply by 2, that is taken here, multiply by 2 and write for only 4 1. Okay, so what you are doing here is writing only for 4 1 the moment you are writing, right? So 2 into you are writing moment. Now how you are writing moment? First Q41 you are writing is the Q41 is the shear flow. Okay, and you can extend this line of action and you can find out the perpendicular distance for this one, and the perpendicular distance what you get, it should be that the perpendicular distance must be 17a sin theta. You can calculate from the geometry of the figure. So the Q41 into its perpendicular distance is 17a sin theta into ds1, and you can again integrate between 0 to 10a because 41 wall length is 10a. So integral 0 to 10a Q41 and 17a sin theta is the perpendicular distance into ds1, and then you can substitute for Q41. Now what is this Q41 again? So you got QS naught, right? So this QS naught you have to add over here. Okay, then you will get actual 41. Okay, so once you get this 4-1 and you can substitute, or else you can do one thing, you can just straight away substitute the distribution for QB41. So what is QB41 we got? So QB41 is equals to this one minus SY by 1152 A cube into 2 by 5 S1 square. So minus 2 by 5 S1 square plus this QS naught we are adding here, so that you have to add here. So whatever it is, so that you have to add QS naught, we have to add and get Q41 and add it and substitute here and integrate between 0 to 10A. Okay, and when you do that, integrate between 0 to 10A and try to find out this SY and SY will get cancelled on both sides because that you have assumed, and then you integrated this right term between the limit 0 to 10A and try to write it, and you're going to get zeta s value. Okay, and for calculating this, and here we got sine theta, that is very very important, and sine theta can be written as sine theta 1 minus theta 2, and which is nothing but sine A cos B minus cos A sine B form you can write. So sine theta 1 cos theta 2 minus cos theta 1 sine theta 2 you can substitute, and sine theta 1 you can get from the diagram as 15 by 17, cos theta 2 you can get it from 8 by 10, cos theta 1 8 by 17, sine theta 2 6 by 10, you can get it from the diagram very easily from the basic geometry of that diagram. And when you substitute all these values into the previous equation, this one, and try to substitute, and you are going to get zeta shear center position as minus 3.35A. Okay, minus 3.35A. What does it mean? If you look at the diagram, zeta s is minus 3.35A. That means from here to here we calculated minus 3.35A. That means it is well inside. That is 3.35. So somewhere here your shear center is going to lie. This is minus 3.34A, 3.35A, minus 3.35. That means it should be well behind the position what we considered, minus 3.35A. So that is what the meaning of it. Okay, which means that the shear center is inside the beam section. So that is how we calculate the shear center for closed section. So the procedure is little complex for this closed section beams because that is what we have to practice more than one time. So you need to practice at least 3 to 4 times to get practiced and remembered with this procedure of shear flow in closed section beams and to find out shear center. So that's it for today's session, and in the next session we see additional problems in shear flow in closed section beams for the calculation of shear center. So thank you everyone for watching.